Hello, once again welcome to our lesson. We want to discuss the chemistry of period 3 elements, and first of all we want to look at the chlorides. Before we took a break for the COVID lockdown, we had discussed the oxides of these period 3 elements. But before I proceed, I would like to encourage you and remind you to observe the standard operating procedures, because the COVID is real. So to proceed, we want to look at the chlorides of these period 3 elements, and we shall begin by looking at the preparation of these chlorides from the different sources that are available to us. The first member of the period 3 of this period 3 is sodium. Its chloride is called sodium chloride, and is prepared by neutralization reaction between sodium hydroxide and dilute hydrochloric acid. In that equation, we have demonstrated that hydrochloric acid reacts with sodium hydroxide to give us sodium chloride and water. However, if the sodium chloride is required anhydrous, that means dry, what we can do, we can either react this sodium with the dry hydrogen chloride gas, and we are able to get our sodium chloride, which is anhydrous plus hydrogen gas as a byproduct. But also we can prepare it by direct synthesis. This is a reaction between chlorine and sodium, and then we are able to obtain sodium chloride. To proceed for the reaction for the preparation of magnesium chloride, there are various methods that we can employ, like you can see in our equations. First and foremost, if it is required not anhydrous or in solution form, or without even caring about whether it is anhydrous or not, you can actually react hydrochloric acid with magnesium carbonate to form magnesium chloride, carbon dioxide, and water. Also, from the reaction between hydrochloric acid and magnesium oxide to give us magnesium chloride and water. However, it can also be prepared from its hydroxide, like those equations are showing. If it is required anhydrous, like we did in sodium, once again, we can use direct synthesis to produce this magnesium chloride by reacting our chlorine with magnesium, and then we are able to get the magnesium chloride. We can also use hydrogen chloride gas. Shall be able to get magnesium chloride solid and hydrogen gas. It's important for us to notice that one of the conditions for these reactions to occur, we need to have heated our magnesium. Aluminium, which is now the third member of this period 3, its chloride is prepared by reaction with chlorine to form aluminium chloride. Of course, we have to heat the aluminium. However, we can also use hydrogen chloride gas to produce aluminium chloride by passing hydrogen chloride gas over heated aluminium. Like we have already seen, aluminium chloride dimerizes in vapor phase. So in our equation here, we are seeing that at a temperature of around 183 degrees Celsius, chlorine reacts with aluminium to form the dimer of aluminium, which we have shown there. So you see you have two molecules of aluminium chloride coming in contact, and where you have the arrows, that is showing us the direction of the formation of what we are calling our dative bond. So I have explained that previously. This is just the purpose of reminding us. The chlorides of beryllium and the iron can also dimerize. So in case you find that, you should also remember that it is similar to that one of aluminium. Then silicon tetrachloride, for it is prepared by passing dry chlorine over heated silicon, and the equation there is showing us that chlorine reacts with silicon to form silicon tetrachloride, and you can see that the state symbol for that reaction, for that product, is a liquid. It's very important for us to observe that. However, silicon tetrachloride has other methods which can be used to prepare it. For example, by heating a mixture of silicon oxide and carbon in a dry current of chlorine, like that equation showing us, shall be able to get our silicon tetrachloride and carbon monoxide as a byproduct. Then the chlorides of phosphorus, there are two majorly. One is phosphorus 3 chloride, which is a colorless liquid. For it to obtain it by passing limited dry chlorine over the more reactive forms of phosphorus, which is white phosphorus, to give us phosphorus trichloride, which is a liquid. However, if we needed the phosphorus pentachloride, this one is a solid. It's a very important reagent in organic chemistry. For it is obtained by passing chlorine over the formed phosphorus trichloride. We are able to get this solid, which is phosphorus pentachloride. Phosphorus pentachloride is a white solid which can also be phosphorus pentachloride is formed, like I've already said, by the reaction between phosphorus trichloride and chlorine. Then disulfur dichloride, for it is a lead liquid which is obtained by reacting sulfur and chlorine. However, one of the conditions is the sulfur is molten, and that's when it is able to react with this chlorine to give us the disulfur dichloride. There is a simpler form of this chloride, which is sulfur dichloride, which is also a red liquid. But for us to be able to get this reaction going, or to get that product of ours, the sulfur dichloride, which is also a red liquid, is obtained by reacting chlorine with disulfur dichloride at a much lower temperature, which is at 0 degrees Celsius. So after knowing how those chlorides can be prepared, we want to proceed and look at the properties of this chloride. So we have summarized many of these properties in this table. First of all, we are showing the elements of the period 3 element, these period 3 elements, and their formulas of these chlorides. Remember, you can easily be asked to write the formulas of these chlorides. So for sodium, it is sodium chloride. For magnesium, it is magnesium chloride. For aluminium, it is aluminium chloride. And for silicon, silicon tetrachloride. For phosphorus, like we have seen, we have phosphorus pentachloride and phosphorus trichloride. Notice the states. Phosphorus pentachloride is a solid, white in color. Phosphorus trichloride is a liquid. Sulfur likewise has 2 chlorides. Physical state, sodium, magnesium, and aluminium are solids. Silicon is a liquid. For phosphorus, we have seen that one of them is a solid and the other is a liquid. And then for sulfur, its chlorides are liquids. Then the pH in solution, sodium and the magnesium are neutral, the rest are acidic. Then the bonding, we have sodium and magnesium, and for them they form ionic bonds, whereas aluminium forms a chloride which is partially covalent and partially ionic, but it's mainly covalent. Then the rest of the chlorides are covalent. Then there we have the structures, J and ionic for the first 2. Then we have molecular, layered molecular, and then the last 2, which is phosphorus and sulfur, for them they are simple molecular. Then if we go into the details of this structure and bonding, we are saying that sodium chloride, from sodium chloride, disulfur dichloride, there's a tendency to move from ionic character towards the tendency to form covalent chlorides. The reason is, first of all, the decrease in electropositivity. There is a less tendency for the metals, for elements to donate electrons for bonding. So as you move from sodium towards the right of the period, electropositivity decreases. So we are saying that sodium chloride is the most ionic, followed by magnesium chloride, and then aluminium chloride is mainly covalent. The reason is it's not ionic, though aluminium is a metal. The reason we have seen previously, but just remind ourselves, aluminium has a high charge or a big charge, a charge of +3 and a small ionic radius. So that gives us a high polarizing power. And like I have previously said, the higher the polarizing power, the higher the tendency to form covalent compounds. Then the chlorides of silicon, phosphorus, and sulfur are purely covalent. And then we are saying that this tendency to move from being covalent, from being ionic to forming more of covalent chlorides as you move from the left to the right of the periodic table in the same period, has a big effect on the melting points of these chlorides. So that brings us to the melting points. Like you can see here, sodium chloride has the highest or the biggest melting point, followed by magnesium, aluminium, silicon tetrachloride, then the 2 chlorides of phosphorus. But something interesting about the chlorides of phosphorus, you notice that phosphorus pentachloride has what I would call abnormally high melting point, and then the trend reduces again as expected. We shall look at that. So here we have explained the trend. It's very important for us to know how to state the trend. So like you will check in the notes to have done that properly. Then the explanation, why is it that sodium chloride and magnesium chloride have the highest melting points of the chlorides? The reason is because these 2 are giant ionic and held by strong ionic bonds. These ones require a high amount of energy for those bonds to be broken. For sodium, the melting point of sodium is higher because sodium has a small ionic radius. we are saying that this is because the melting point from sodium chloride to magnesium is because magnesium ion has a smaller ionic radius compared to sodium. Sorry about the other line previously. And for that reason, having a smaller ionic radius and a big charge gives it a high charge density or high polarizing power. And what does that mean? High polarizing power, like we previously said, tends to bring about covalent character. So the sodium chloride bond is more ionic compared to the magnesium chloride bond. The reason is the magnesium chloride has that tendency of covalence brought about by the high polarizing power of magnesium. Then aluminium chloride has a lower melting point than the rest of the magnesium and sodium. The reason is we have already talked about. It has the smallest ionic radius and a very high charge. That gives it a high polarizing power. As a result, high polarizing power brings about predominance in covalency. Then silicon tetrachloride is covalent. Its molecules are held by weak van der Waals forces of attraction. And we have previously said that the van der Waals forces of attraction are mainly affected by what we are calling bond polarity and molecular weight. So if you look at the sizes of these molecules, the size or the molecular weight will determine the strength of these van der Waals forces of attraction. However, we have an abnormality somewhere. I'm calling it an abnormality in quotes. Phosphorus pentachloride has an abnormally high melting point of around 160. Our trend was expected to be decreasing, but why? The reason is because at ordinary temperatures, we have ions of which we are showing here in our slides. Those ions kind of bring about ionic character in phosphorus pentachloride. Because they are brought about ionic character in phosphorus pentachloride, that gives it tendency to form ionic bonds. So as a result of that, we know that ionic bonds require high amount of energy for them to be broken. So the melting point is also going to be high. Disulfur dichloride and sulfur dichloride form simple molecular structures held by weak van der Waals forces of attraction. Van der Waals forces of attraction are weaker forces of attraction compared to the conventional covalent bonds and the ionic bonds. So like we have said, the two factors which affect the strength of van der Waals forces of attraction are bond polarity and what we are calling the molecular weight. So for that reason, you will see that there is that tendency for the melting point to decrease as we move from the left to the right of the periodic table through period 3. So after we have learned the structure and bonding, we want to proceed and look at the chemical reactions of these chlorides or period 3 elements with water. First and foremost, sodium chloride is neutral. So when we put it in water, it will dissociate because it's a strong electrolyte to give us sodium ions and chloride ions. Then for magnesium, it gives us magnesium ions and chloride ions. For these two, the solutions are neutral because they are formed by the reactions between strong alkalis and strong acids. Aluminium chloride undergoes hydrolysis. This is an interesting one because we can see here that hydrolysis is basically the reverse of neutralization. You can see the chloride of aluminium reacts with water. So aluminium chloride is a salt, water is the product of neutralization. So they are giving us a base, which is aluminium hydroxide, sparingly soluble in water. That's why the state symbol is solid and HCl. So that's the opposite of neutralization, which gives us hydrolysis. So we are producing an acid. So the ionic equation can be written as we have shown in the alternative of the molecular equation. But this is an interesting one because for this particular reason of the hydrolysis of the chloride of aluminium, which we are going to look at later when we do the chemistry of aluminium, if you added the sodium carbonate to a solution of aluminium chloride in water, we are able to see an effervescence. The reason is aluminium chloride undergoes hydrolysis to form hydrochloric acid. The hydrochloric acid reacts with the carbonate ions from the sodium carbonate to give us carbon dioxide. But we are also able to see white precipitate. The white precipitate is due to the formation of aluminium hydroxide, which we are seeing in our equation. Like I've said, we shall discuss this in details later on. Then silicon tetrachloride, for it reacts with water to form silicon oxide and hydrochloric acid. This reaction results in the formation of an acidic solution because we are forming hydrochloric acid. I would like you to notice the trend in the formation of acidic solutions. For sodium chloride and magnesium chloride, we said when we put them in water, their solutions are neutral. However, as we move towards aluminium, it is acidic. Then for silicon, we are also realizing it is acidic because we are forming hydrochloric acid. Phosphorus trichloride, for it reacts with water to form phosphonic acid and white fumes of hydrogen chloride. The resultant solution is also acidic because you have two acids which have been formed. Then the tetrachloride will also give us phosphoric acid and then hydrogen chloride, but these are produced as white fumes. Likewise, the solution is acidic. So there is a tendency to move from being neutral towards acidic as I move across from the left to the right of the periodic table when I'm considering the chlorides. Then disulfur dichloride reacts with water to form two acids. First of all, it forms sulfurous acid and then hydrogen chloride gas. And then the other product is sulfur. So this one is given off as a deposit, yellow deposit. So if you are carrying out this reaction in a test tube, you'll be able to see that the yellow solid is being deposited. So basically that is what we wanted to discuss, and thank you for your time. For more information, you can check out those websites.